Foundation Models for Embodied Decision-Making Agents, Part 5. Today I'm discussing two papers and one just comments on Sora, which is a video generative model released by OpenAI a few days ago. What's in common here is that we can see the power of Gen AI in certain relatively unrelated problem sets. One is video compression, one is math problem solving, and one is generating data sets, whether it's in math problem solving or whether it's in robotics. The point is that with Gen AI, we have the potential now to generate massive data sets that can be used in simulation, for example, in robotics. This is not even on podcast. It's February 19th, 2024. This is Krim Delco. There's no updates. It's President's Day. The markets are closed for the year. We're down 12.4%. The market is up 5%. We're underperforming by 17.4%. So the three things I want to discuss today are all related to foundation models for embodied decision-making agents. And let's start with the first one, that is Sora. Sora is a video generative model that was released by OpenAI. It excites a lot of people, and just go on X or go on YouTube and you'll see the power of the generative videos. What is generative video AI? What does that even mean? It means that you can prompt either with text or with video or with code, or you just prompt a scene and then the scene gets reproduced on video. That's what it means. And Nathan Lambert, for example, in his discussion of Sora, talks about the potential for gen video for robotics, right? You can have generated scenes for simulation. And this is something we've been talking about at Orange Capital Partners for a while now, that we believe that the potential for end-to-end learning in robotics is massive. But the problem, of course, is that you don't have, in real time, having a robot learn, particularly using model-based or off-model-based reinforcement learning. Either way, it's relatively difficult because of the constant interaction and the potential mistakes that the robot makes. So in simulation, you could potentially solve that problem. You could also use some offline reinforcement learning, maybe. The potential, the point is this: like, we can generate our own data sets. And with our own data sets, we have the potential to solve some of the more prevalent robotics problems. I think this is all I want to say for now. I think it's useful to think about the potential here for the data set generation. And then once that train of thought has been thought through, then of course all the nitty-gritty engineering problems come up. Okay, how do you generate the data set in a way that it's useful for the kind of problems that you want to solve? But in general, we can think of data generation in robotics as driven by something like Sora and the models that are coming in the future, which will probably be a lot more powerful. Now, related to this is the first paper I want to discuss today, which is a paper published by NVIDIA, and it's about math problem solving. And what the authors are doing here is pretty interesting. They're creating a problem solution tuple data set by using a large language model, in this case Mistral, to generate a solution. So they prompt a problem and they use code to generate a solution, create a data set, and then use that data set to train the model to actually solve the math problems without, the sort of, sidestep of code. I think, again, the power of this paper is one, of course, in the methodology, but also just philosophically. Like, you have the potential here to generate your own data sets, in this case, a math problem data set, that then can be used to further train the model to become better at solving math problems. The third paper I want to discuss is data compression, and I think this is really super interesting. So what's going on here is that in this paper, the authors are discussing a methodology to extremely compress video by, again, taking an original video, compress it, and then use snippets of that video and then generate the rest of the video. So use generative AI as a sort of stored memory to reconstruct the video. This is something Jensen was talking about in one of his recent talks when he spoke about the power of generating scenes or rendering scenes or generating generally, like we humans have this ability. Like if I tell you I was surfing yesterday in Half Moon Bay, you can imagine that scene, particularly if you've been there, particularly if you've surfed yourself. You can imagine, you can see me surf there, right? I don't need to show you pixels. So in a sense, you have a massively compressed form of video or imagination or whatever we want to call this. But we can use the same methodology for video compression, right? I just prompt a very small snippet of a large video data set, and then the rest gets compressed. So, and the rest gets generated. So this is, I think, it's a really powerful idea, and I want to. The reason I chose this paper to present it here in this podcast series is because I think this is just the beginning of a massive shift in synthetic data creation, video compression, robot learning, like simulation, like all of these fields have one thing in common, which is we can now generate our realities either by using real prompts from real original data, or even just generating prompts out of the blue. But again, the point is we can generate our own data sets to then further learn, either whether it's robotics learning or math problem solve learning, or we can use it for massive data compression. As a side note here, I've spoken about this a couple of months ago in one of the electrical engineering seminars at Stanford. There was a lady from the University of Pennsylvania, and she was talking about neural data compression, learn how to compress data in a data-driven approach. Now, in her presentation, she was giving sort of an information theoretic context into data compression. But what I took away from there is, first and foremost, data compression and learning are basically two sides of the same coin, right? How do you compress data? Well, you learn about the data, and then you can denoise it and get rid of what's not important. I mean, that's fundamentally how you can compress data. And I think what this paper here brings to the table, which is really new, is on top of that, this idea of learned data compression has been around for a while, of course. But what comes here is the fundamental idea that Jensen was talking about, which is that imagine I tell you I was surfing yesterday in Half Moon Bay, and you can then reconstruct that picture because you've compressed it, you've been there, you've seen that, you have it in your memory. Now, the way the paper actually works, the mechanics of the paper are the following: that you have you take the original video, and then you kind of compare. You take frame by frame. You look at, okay, from this frame onwards, what if I just generate the video, and then you compare what you generated with the original, and when it's good enough, defined by a certain threshold, then you really get rid of the original and just keep the compression, keep the learned compression. So think of the compression as a weight matrix which has enough information to reconstruct the video, and therefore has orders of magnitude less, takes orders of magnitude less memory space and data transmission space and all of that to actually store that particular video. Now, in a way, you can think of this is not fundamentally different from existing data compression techniques, because pretty much every data compression technique follows the same principle, which is, okay, how is my scene going to change? And if my scene isn't changing much, I can just sort of disregard the pixels that are coming or the frames that are coming in the near future. So if I have a scene of a forest, and let's say I have a shot, sort of an overshot of a forest, and it takes about 20 seconds until an airplane shows up, and then there's, I don't know, a combat scene or something in the movie. I don't need to transmit all the 20 seconds of that particular forest. I can cut it, right? And then whenever something changes, when there's a new feature or a new something new in the video, then I have to use a little bit more data. So in that sense, this is not very different. I think what's different is just the way that the reconstruction is done. It's done by Gen AI, and therefore it's using a weight matrix to reconstruct the video instead of actually stored encoded video pixels or frames or whatever the unit of storage is. So that's the difference. And I think this is really interesting, again, in that University of Pennsylvania presentation that I attended a couple of months ago at Stanford. That was discussed from an information theoretic approach. If you look at this paper that I'm discussing now, the paper that talks about this extreme compression, this paper goes through 24 of video compression papers, discusses methodologies, and really introduces this new idea of Gen AI as a tool for video compression, which I think is really powerful. So to summarize, I think we have, in a sense, one idea across several different applications. The idea is that we can use Gen AI to reconstruct some of the reality that we need for whether it's math problem solving, whether it's robot learning, whether it's video compression. In the end, we use Gen AI, we use weight matrices that are trained, learned as a compression of knowledge to then be able to reconstruct whatever it is we need, whether it's math problems, tuples that of problem and solution for math, whether it's video compression that we can use the Gen AI to reconstruct certain parts of the video, so that way we can save ourselves certain data that needs to be transmitted or need to be stored, and then also the Sora conversation inspired by Nathan Lambert is there. I think the idea is, okay, we have a video generative model which is pretty good. If we extrapolate this, and also we need some faster processing times and things along those lines. But once we are on that path, I think we are starting to crack robotics and the ability to use simulation for robotics learning. Thank you.